Hello, hello, and welcome to the tower. Uh, Let me check before we start because I'm not sure if we are using the right sound. I don't know if it's working well. Just 1 second. It should be working now. Okay. Okay, it seems the sound is not in good quality. Let me fine-tune something. This is what happens when we are live. So okay, perfect. Okay, now it's solved. Thank you very much to all those people that are watching this first interview from the tower, to all the sentinels that are there watching this video. First of all, don't forget to subscribe to this channel to receive the alerts for future interviews and future videos, and also help us support the promotion of this content in YouTube. It's very easy. It's just a button with subscribe and a bell that you can click to receive the alerts. Today is a very special day, as I told you before, because we have our first interview in this channel. The audience is growing, and we have a very important innovation to discuss with David Mallasén. David is now in Switzerland and is a person working in the University of Universidad Complutense de Madrid. Is in Spain, but he's now working in Lausanne in Switzerland. David is a computer science and mathematics graduate, and he got a master's degree in embedded systems in Sweden, and he's now a PhD candidate in computer engineering in Complutense of Madrid. Welcome here, David. Now you are live. Everyone can see you.
Oh, hello, everyone. Thank you for having me.
And here we are discussing, we're going to discuss today about one of the innovations, your main innovation in your research team that surprised me when I read about it in a journal. It's an innovative way to represent the digits, the numbers, the information in computers. So we are all accustomed to use computers. We know everyone has heard that computers use binary code, ones and zeros, but then inside that there are a lot of protocols, a lot of rules to represent data, to represent the pictures, the movies, the information that is inside the computer. And you have, your group has built a computer called PERCIVAL, which is the first to use an innovative technology called POSITS. So why are these representations, different representations, and this POSITS representation needed for numbers in computers?
I mean, first of all, I think numbers in general behind computers, they're basically what it's used to get results, right? We have a computer, we want to give it something, and we want to get something back. But this is not for free. So just as a small motivation, as you can see, for data centers, which we use every day, we have our own devices, our laptop, or our smartphone, or whatever. But most of the actual computing is not done in our devices, but it's done in data centers from Google, Microsoft. or whatnot. So these data centers have an energy cost, which is huge, and it's rising yearly, basically. Just as so you can have an idea, the whole data centers around the world use more electricity than entire countries. So you can see in this picture on the right that their energy cost could be the same as South Africa. So it's huge. And just also so you get an idea, AI models, which are used everywhere nowadays, and you've heard about ChatGPT and all of the innovations this bring. But just training a single AI model can emit as much carbon as 5 cars in their whole lifetimes. This includes also the fabrication process of the cars. Training a single AI model.
And we can imagine now, ChatGPT is in everyone's mind. Everyone is using ChatGPT even for free, and doing experiments and asking silly questions. So this is very important, because behind that engine there is a lot of energy consumption. So you maybe, when you are using ChatGPT or any other AI tool for your no special purpose, just for enjoyment, you are not maybe you're not aware that you are polluting the environment and contaminating, because you're consuming energy, and this energy is produced to power some large data centers. And there is a problem with data centers, as you said before. There is a forecast. You showed some pictures. There are some forecasts suggesting that this is going to be a real concern in the future for countries, because everything will go digital and data centers are continuously growing. And it's very interesting that you introduced your innovation relating to the energy consumption, because it's a real problem.
Sorry, yeah, even the live emission that we're doing right now, just to bring the video from our computers and our cameras to all around the world through, in this case, YouTube, that takes a lot of power, and there's a lot of algorithms basically treating the video image, compressing it, and doing a bunch of processing behind it, and then sending it throughout the internet. So yeah, basically numbers are in the base of all of this, and if we can optimize how the computer treats numbers, how they're represented, and how they perform some computations like addition, subtraction, multiplication, then we could affect the actual cost of everything behind data centers. And not only data centers, we also have IoT devices, Internet of Things. So small sensors that could be distributed around cities or around many other places. And those usually rely on batteries. So we also want those batteries to last longer. And a way of doing this is by optimizing the energy use of the numbers behind all of these computations.
Okay, and what is the difference? Because we have started speaking about POSITS, but what is the difference between POSITS and the classic floating point numbers? Before answering to that, for those people that don't know what floating numbers is, please think that you have to represent all numbers in your mind, and all numbers means the number integer numbers, for example 1, 2, 3, 4, but you also need to represent the numbers that have decimals, so a payment, for example, with cents. And also you need to represent numbers that are more complex, like the number p, for example. And computers traditionally used a format called floating point, that is a registry, a record in the computer with some rules to represent all these possibilities to that numbers provide. And you are suggesting now, you are proposing a different representation that claims to be better, called POSITS. What is the difference?
Yeah, I also have a couple of slides just showing a bit of the motivation of what you just said. So as you mentioned that there is integer arithmetic, which just so you all know, it's 0, 1, 2, 3, and also -1, -2, -3. What is good about this arithmetic? If you have a binary representation of this, you can represent all of the numbers within a range because we don't have infinite bits in our computer. So you can imagine that just with 3 bits, which is 0, 0, 0, all the way up to 1, 1, 1, you can represent the whole numbers inside the range, for example, 0 to 7 or -4 to 3. These are 2 different encodings of integer numbers, as you can see there in the bottom left, you have normal unsigned numbers, which is 0, 1, 2, 3, 4 with the binary representation. But also there in the middle, for the same bits, the meaning can be slightly different. You can see that for 1, 0, 0, in the left it's a 4, but in the right it's a -4. So just with the same bits, depending on how we want to represent them, these can have different meanings. And just so you know, these representations are arbitrary. You could say that 0, 0, 0 means 500, but we need efficient ways of encoding this and of decoding. So how to go from a series of zeros and ones down to a number that we want to represent and back. We have 7, and how do we encode it back into zeros and ones? So yeah, as you said, we don't only want to not only do we want to use integers, but how do we represent 1.5 or square root of 2 or pi or whatever other more complex numbers, which are used, for example, in the live video that we're doing and scientific computing and simulations in many things. So what's different from real numbers than from integer numbers that we need something different? We have very large numbers. For example, in physics, Avogadro's constant, which goes 10 to the power of 23. That is a 1 and 23 zeros. So it's a very, very, very large number.
Very large.
Yes. And also very small numbers at the same time. So the range is huge. So we can have, for example, Planck's constant that is 10 to the -34, which is 0.34 zeros and then a 1, which is 33.
Okay. And these numbers, for those people that haven't heard about it, are used in many things that impact our lives. For example, Avogadro, as you mentioned, is absolutely used in chemistry. So all chemists around the world producing the washing substances for home, cleaning, creams, cosmetics, etc., have to deal with Avogadro's constant, and Planck's constant is used in physics. So in all what is related to, for example, nuclear energy or even satellite communications, etc., use Planck's constant. So it has to be used in computers. It's not an empty example.
Exactly. So we have this, and we call it dynamic range, which is the difference between the largest and smallest number, basically, or how wide is our representation. But we also need accuracy. There are infinite numbers in any given range. So between 0 and 1, you have infinite numbers in there. So and we cannot represent them all because we don't have infinite accuracy. For people who are interested, you can search for the cardinality of infinity. This is some math stuff that is actually quite interesting. The problem here is that we only have a finite number of bits to represent an infinite amount of numbers. So we need always this trade-off between dynamic range, which is how far we can reach, and accuracy, which is how deep we can go in for a small number. We want to represent 0.000001. That is going to require a lot of accuracy. So, like you introduced before, the normal way of doing this is with floating point numbers, which is the most widely used format. It's in every device that you can imagine, and it was established in the 80s, but it has been revised many times since. And just so you get an idea of how we can represent numbers, they are composed of a sign bit, then some exponents and some fraction. The sign, positive, negative, we all know this. Exponent is how large is this number. So this allows for a greater dynamic range, and the fraction is how many fraction bits. This is related to the accuracy. The more fraction bits, the more accurate we can be when representing a number. And they're just, if you're curious, it's the way of going from this sign, exponent, fraction down to a real number.
Okay, so this is a way to use the bits. The bits, one bit is 1 0 or one, or a 0 or a 1 in a computer record. You have a number of bits, obviously, and everyone has heard and knows that he has or she has a 32 bits computer or 16 bits, so the number of bits is there in each computer is limited, and with this formula, with this coding, with this way to arbitrary, as you said before, this is arbitrary. Someone decides, okay, we are going to represent the number whatever, the number with decimal value here in this formula is translated into bit 1, bit 2, bit 3, bit 4 in this sign, exponent, and fraction. So it's a way of coding this number in a computer.
Exactly. But what was proposed a few years ago by John Gustafson, it was not by us, was the POSIT arithmetic, which is another way, a different way, because as we mentioned, this is arbitrary, but we want to make it efficient. So this is a different way of encoding real numbers. So as you can see, this is slightly more complex because it adds a new field, which is the regime. You can see it there in yellow or orange. And this is variable length. So before we had a fixed length exponent, which means that it always has the same amount of bits, and a fixed fraction, which always has the same amount of bits. Now with this regime, we can make it longer for some numbers and shorter for some numbers. This also allows to have a shorter or longer fraction. Okay. So this relates back to the trade-off that I mentioned between dynamic range and accuracy, how wide we can go and how deep we can go for some numbers. And as before, the way of encoding is slightly different, but it's a formula. You can just plug in the numbers, and it gives you a result back.
Okay.
This is a bit new. It can be a bit confusing. So I also prepared an example, maybe, so
okay.
We can all follow
that
it.
was a question I have. Why this is better, or in what cases it can be better to use this representation instead of others?
Okay, so the cases depend a bit on the numbers that are used. So let me skip for a moment the example. We can go back to it. And I can show you a graph that we usually use to compare floating point numbers and POSITS. So it seems a bit complicated maybe, but it's not. On the horizontal line, we have the exponent. So we have exponent 0, 20, 50, 100, whatever. And on the vertical line, the y-axis, we have how accurate the numbers are for that exponent. So as you can see in the yellow area here in the middle, I don't know if you can see my cursor, but here in the middle, we can get more accurate numbers with POSITS. So we can go deeper into these numbers when we have exponents between -20 and 20. This, so everyone can understand, is for numbers up to 1 million and lower, and up to 0.000 10 to the -6, so 6 zeros and 1.
Okay, and this is with the same amount of bits?
Yes, with the same amount of bits, depending on how we encode them or decode them, how we think about these bits. We can either use the floats, which is shown here in blue, or POSITS, which is the pyramid shown here in purple.
Okay.
This is for 32 bits. So for 32 bits, we can see that in the middle, we can be a bit more accurate, but in everywhere else, floating point wins.
Okay.
But if we go to 16-bit, so smaller numbers, which are also more efficient for some kind of calculations, we can see that POSITS win in most of the cases. So in the center, we still have more accurate numbers. But also if we go to the sides, which is the dynamic range, how far we can reach, we see that POSITS have about 3 times as much reach as floating point.
Okay.
So
this raises a question for me. So it seems you are reviving old computers that work in 16 bits instead of 32 or 64, or the computing industry always try to increase. The same in all industry, everyone tries to increase and do more and bigger. So this gives a new life to old computers, but in reality it's probably interesting to explain that now there is a trend to produce computers with very little power, very low complexity, as you said before, for Internet of Things, for artificial intelligence, for blockchain. All these technologies are based on very basic arithmetics that can be done by an old computer. So if you can build an old computer that is much more efficient, you will be able to build a lot of devices for artificial intelligence, for blockchain, for Internet of Things, probably much more efficiently with POSITS than when floating.
It's not actually with older computers, because they will use a different technology. Like we've heard, the technology nodes, 22 nanometers, 16 nanometer, 3 nanometers now. So it doesn't mean that with old computers we can use them again, but it means that with less power we can compute the same numbers. It has to be with newer computers, because in this case, for example, POSITS are not present in laptops or in mobile or in phones yet. This is part of our proposal of bringing POSITS to hardware. But as you mentioned, there is a trend to go bigger, to have 32, 64, even some people talk about 128 bits. The thing is that when you have these larger numbers, not only they use more power, but they are bottlenecked by memory. So usually you have a CPU and then you have a memory, and you need to communicate between these. So there is a big bottleneck between, RAM or just a normal hard drive and the CPU, because the CPU is much, much faster. So if you have to transfer less data between a CPU and the memory, you can make all of the computation even faster. So there's always trade-offs in these situations, and depending on what you want to do, you can use one or the other. Yeah.
Perfect. Okay, so you were about to show us something else?
Yes, I prepared an example, in this case for POSITS, so people can understand how from a series of zeros and ones, we can get to an actual real number, so an actual value. So this is for 16-bit POSITS, so there are 16 zeros and ones there, and we're going to see what number this is, okay? So firstly, we will look at the first number on the left. and this is the sign bit, and we see that it's a 1. Okay, then we have to look in the case of POSITS for the regime. So this field is a series of 1s followed by a 0, or a series of 0s followed by a 1. In this case, the other way, as you can see, we have a series of 1s followed by a bit flip, which in this case is a 0. This is the variable length that I said. We could have a lot of 1s and then a 0, or just a 1 and then a 0. It could be very short or very large. Then we have a 2-bit exponent, which in this case is the 1, 0, the next 2 bits, and all of the rest will be the fraction. So in this case, the fraction is composed of 8 bits, but it could be more, it could be less. And then we have the same formula that I showed before, but for this specific number. We have the formula on the left will give us the final value of this POSIT number. The formula on the right, which is the R equals blah, 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 that is to compute the regime, depending if it starts with 1 or with 0. There are two ways of decoding this. So we have a sign bit of 1. So everywhere there is an S of sign, we just substitute by a 1. The exponent is 1, 0, which in binary is 2. So in the exponent, in letter E, we have a 2, there in blue. And also the fraction, it's these 8 bits. That number in binary is 150, as you can see in green here in the bottom. And there are 8 bits. So the fraction will be 150 divided by the largest number, which is 2 to the power of 8. And finally, the regime. So we have 4 identical bits followed by a bit flip. So k will be equal to 4. And since the first number is a 1, we use the formula here in the bottom. It's k minus 1, 4 minus 1, which is equal to 3. This is normal formulas like we used in school. We just have some numbers, we put them in the formula, and then we get the final number. The final number in this case is that one over there, which is kind of a small number that we can encode with 16 bits using POSIT arithmetic in this case.
Mm-hmm.
So yeah, this is a way just so people can see. I mean, this is not straightforward. Maybe you have to stop a bit and see what is going on, but it's a way to encode some numbers.
Okay, now we have seen a lot of mathematics for the moment, a lot of formulas, a lot
Yes.
of theory, and I presume that many others in the audience want to watch something tangible about the prototype, about PERCIVAL. So that computer that you are producing or you are building, what do we know? What can you show us, and what can you tell about the PERCIVAL computer using POSITS?
Yeah. So we have these numbers, but where are they actually? I mean, inside a computer there are many things. So where are exactly these numbers? So usually we are all used to a desktop, which you have your actual PC. But you also have your screen, your keyboard, mouse, and whatnot. So it's quite obvious that these numbers are going to be inside the actual computer. But the actual computer has many things. It has the RAM memory. It has the power supply. It has hard drives where you store all of your data. But it also has the CPU. It's the central processing unit. It's let's call it the brains of a computer. But inside this CPU, there are also many things, and it's quite a complicated piece of hardware. Here we can simplify it a bit. And inside the CPU, there are these things called arithmetic units, which are the pieces of hardware that have to do all of the number crunching. So all of the computation using these numbers. So it is inside these arithmetic units that we can have either integers, normal floating point numbers that we have in most CPUs, and also where we wanted to add POSIT numbers, right? So we propose to grab a CPU, a CPU core. In this case, it was one that's called CVA6, which was developed under the PULP platform. This is part of it's partly done by ETH Zurich, the university in Zurich in Switzerland, and also by University of Bologna in Italy. And now it's maintained by an open hardware group. So we took this CPU, which is open source, it's open hardware. You can go grab it, modify it, and do whatever you want. So we did that. We grabbed this open source CPU, we modified it, and we also gave it back as open source to the community. If you go to that URL there, all of the code, all of the hardware for our POSIT numbers is there. And this is a bit more complicated jargon. You can see in the bottom kind of the diagrams of the parts inside the CPU that we modified and where we added the POSITs. You can see in orange there the POW, which is the POSIT arithmetic unit, which is the part inside the CPU which is in charge of computing with POSITs. So what we did is grabbing this CVA6 core, which can run Linux, which is an operating system. You all know Windows or Mac or Android in your phones. Well, there's also Linux, and this CPU can run this operating system. And we added all of these POSIT operations in parallel to normal floating point numbers because, I mean, we are researchers, we're at a university, and what we wanted to do is compare them. So compare POSITs and floating points to see which ones could work better in some cases, work better in others, and what are the pros and cons of these arithmetics, right? I don't know if this is a bit too technical, but yeah, this is what we wanted to propose, a way to have these POSIT numbers not only in our minds or in a whiteboard, but also in actual hardware that we could touch, that we could run our experiments on.
Okay. And this is a computer that you built on something physical or just as a simulation?
No, we did build them. We built it also on something physical. So let me find an image that I had here. This is for something that I had prepared for later, but you can see there in the bottom there is a board. This is an FPGA, which is a field programmable gate array, where we can design our hardware, describe our POSIT units, and bring them down to actual hardware, to an actual chip that will execute the hardware that we have described. So here you can see the board, and we had it connected to my laptop, to a normal PC, and we could run some code. You can see there in the screen. I don't think you can read much, but you have there an operating system, and we could run POSIT numbers on that. That is actually where we are testing now all of our prototypes.
Okay. And how do you think that this innovation can impact the future of digital systems?
Yeah. So there are always pros and cons to whatever you're trying out, especially in research. And for POSITs, we saw that there were pros in certain areas and also some cons that we also have to deal with. But I think we have kind of the way to go with that, right? So what we are looking is to reduce the errors of computation. If we can make them more efficient, maybe we need less bits to compute the same thing. If we use less bits, as I mentioned before, that is going to be more energy efficient because we don't have to transfer as much data between memory and the CPU. There's also some things that maybe we've all learned in school, and you know that A plus B is the same as B plus A. So it doesn't matter if you add 1 plus 2 or 2 plus 1. It's always going to be 3. Well, actually, if you use a floating point, this is not the case. Because of the way of how numbers are represented, A plus B is not always the same as B plus A. But in POSITS, this is. So we can always have the same the same results, even if we compute stuff in different machines. So there are a series of advantages, and also we have no performance degradations. But there are also some cons, which in our case was we need a bit more area, so a bit more silicon in our chips, and at the unit design there was also an increased power consumption. This has this impacts part of the execution of the code. The thing is that also just to work into energy efficiency and to see where we can actually impact, like in real life, where we can actually use these numbers and have some advantages. So when you move a number from, in this case, DRAM, which is RAM memory, to a CPU to use it, this will cost around 200 times more energy than actually performing an addition. So just by moving the number, you need a lot more energy than just performing an addition on that number. So if our addition requires a bit more power, but we don't have to move as much data because we can use smaller numbers, we will end up with energy savings because we need to use much less energy to move data, and then the actual computations are only slightly more power hungry. So this is especially both for data centers and IoT devices, as we mentioned at the beginning. I mean, data centers, they need a lot of number crunching, they use a lot of energy, and also Internet of Things, you need the batteries to last a long time, so you want everything to be as energy efficient as possible.
Okay, so you are positioning in both ends, in on the one end on battery powered systems that are very limited in energy supply, and on the other end on very large systems that consume a lot of energy. So it's and that is the question about the benefits and the reason why we are speaking today here in the tower about the POSITS technology, because somebody has to do something with that. We have a problem in large data centers, as we said before, and we also have a problem in battery operated systems because some IoT devices need a long life without replacing or charging the battery. For example, environmental sensors or sensors that are sent to the space or even to the moon. Many devices, small devices, are very limited in the power they can use, and this can represent an important, a significant leap into these new applications using the POSITS technology.
Exactly, that's the beauty about numbers. I mean, they're not always seen, but they're always there. So you have numbers everywhere, both in very small chips, very small IoT devices, and also in data centers. Since this is a thing that's everywhere, if you manage to make them more efficient, you're basically impacting most technologies out there. We just have to find the right applications, the right use cases for these devices. So this, as you mentioned, we target both edge devices and large data centers, but also they could work on laptops, on whatever device. And what we saw at the beginning, like there are clear theoretical advantages, especially in low precision, which basically includes sensors, biomedical devices, wearables, and these pieces of these small chips are actually in the billions all around the world. They're present in whatever we can think of. I mean, in coffee machines, you can have them in a fridge, in smart appliances. So we can make all of those chips, let's say, a bit more efficient. And you've also mentioned artificial intelligence, which is like the big thing right now, and also POSITS could impact this part of artificial intelligence. Theoretically, these numbers would work very well because the pyramid that I showed of the accuracy of POSITS actually matches the distribution of values of the numbers that are used inside the neural networks. However, there are some particularities of AI, and the current trend, what people are researching into, is not using floating point, but some approximations using integers. So we don't know exactly if POSITS could be used to boost artificial intelligence. It's one of the areas of research and one of the areas in which we have to work a bit more to see if this could be done.
Okay, very good. We have one question from our audience, from Jose V, and he's asking, why have you designed your prototype using Linux, and if you are thinking of using other more usual computers like Android based or Windows?
Actually, Android is also based on Linux. I mean, we think that Linux is not used anywhere, but most of the data centers actually run Linux. Most of the big compute cloud uses Linux, and also Android. So actually our phones, or most of us use Linux. The thing about Linux is that it's open source, so you can tinkle with it, you can modify it. And in our case, for embedded platforms, which is devices that are only used for a specific purpose, Linux works very well. There are some Linux images, some distributions of Linux, where you can target them for whatever for whatever hardware you want. So in this case, we had the CVA6, which supported some kind of embedded Linux operating system, and we just used the same thing. It's the good thing about open source. We didn't have to design a new operating system where we could run our applications. We could reuse both the actual CPU, the actual hardware, and the software part, which in this case is the operating system. I guess in the future, if you had, for example, POSITS inside, let's say, an Intel CPU or an AMD CPU, you could run Windows on top of that, like no problem. You just had to make this Windows compatible with the hardware where we can have POSITS.
Okay, and also for those people that haven't heard about Linux, probably more than 99% of the websites are running Linux. The data centers are running Linux behind, so you are not using Linux, but the website that you are receiving this computer is using Linux. And also for IoT, for small devices, you mentioned Android is based on Linux, but also any small device, probably if you have one weather sensor at home, or even your Wi-Fi router at home is using Linux, so it's everywhere. Maybe some people don't hear about Linux frequently, but they have probably one Linux device in less than 5 meters from them.
Yeah, also some of these very, very small devices actually don't use an operating system, and they run what we call bare metal code, which is code that runs directly in the CPU without the need of an operating system that does a lot of tasks behind us that we do need, for example, for a laptop or for a data center. But small devices will not have the need for an operating system. However, for our purposes to test some applications, it was more comfortable to have an operating system where I can just say, okay, run this application, and the application runs. I mean, we have also tested some bare metal applications without an operating system, but yeah.
Okay. What are you doing now? What are you researching now?
Yeah. So right now, as I mentioned, we had PERCIVAL, which is a CPU, a core that is able to run POSITS. But we also want to design accelerators. So accelerators, let's say, are small CPUs that run on the side, and where you can offload some of the computation. So imagine you have to do a lot of operations, a lot of number crunching on some data. You can just offload this to a more efficient device. For example, a GPU, which we most know, like a video processing. This is actually an accelerator. So we want to design as well, we're also working on that, to design accelerators using this POSIT representation. And with all of this hardware that we're developing, what we want to do is to compare the normal floating point, the IEEE 754 floats, versus this POSIT number. We've compared them and used them in several areas, and one of the latest one was in scientific computing. So, for example, for the weather forecast, for physics simulations, chemistry simulations, these are usually run on large supercomputers on data centers. And as you mentioned at the beginning, usually these are run using 64-bit, so larger numbers that can have more accuracy. So we've been trying to test POSIT numbers on those, and that's a work that let's hope will publish shortly. But also integrating these accelerators, these pieces of hardware, into system-on-chip design. System-on-chips are like a big, let's say a big chip that not only has the CPU, but also has some accelerators, some in-out devices, some memory, and so on. Why do we want to integrate them into these system-on-chip? Because they are used in both deep neural networks, AI, and whatnot, but also in biomedical applications. This is used at hospitals to detect some diseases, for example. Also for image processing, for example, in the live video that we're doing right now, for signal processing, for data that goes to satellites, for example. They are used in many cases. So this is basically our lines of research right now at Complutense.
I have one question, because precisely today I have my new book published in the US about the metaverse, and I just wanted to know if POSITs can also be beneficial for the processing and the creation of virtual 3D environments, these graphics, and especially, the real challenge in metaverse applications or in immersive application is what is called the mixed reality. We have a video here in the tower explaining about virtual reality, augmented reality, mixed reality, extended reality, all the technologies about 3D environments, and I invite you, all the audience, to check it. Is there in the library of the channel. The real or one of the most challenging problems in XR is mixed reality. So is processing the environment so quickly and with enough accuracy, so the individual, the person that is moving virtually in that environment can interact with the environment. Now, most computers only show or you are in a fully virtual environment, so it's like a game. You are just playing in a completely virtual world, and you use your remotes or whatever to move there, or you are watching something that is a realistic environment. It's like Google Street View we can imagine like that, and we are moving there, but we are not able to interact. We cannot push a door and then the door opens. And this mixed reality where the reality, the physical reality and the virtual reality combines and interact requires a lot of power to process all these 3D points, 3D representations in real time. Can POSITS do something to this benefit or not?
I guess so. I mean, depends on exactly the applications, but this simulation, no, this processing of images of 3D scenarios, this is done in data centers. Obviously, you're not doing all of the number crunching in your smartphone or the wearables that you have while you're experiencing this metaverse. But yes, in all of the computations behind this image and simulation processing, I'm not sure in this exact case, but probably they also have floating point numbers behind it. And if you could make them more efficient with POSITS, this could reduce the energy cost and in general the cost of exploring this metaverse. Yes.
Okay, we have another question from the audience. One sentinel is asking, Alberto is asking, what are the main problems you are facing when developing this technology?
Yeah, the problem is that you cannot find POSITS in normal computers. So we have to develop new hardware for them. So yeah, you can try them out, but to try them out you need actual hardware. So the main problems we're looking at is that we need customizable CPUs. You need to be able to have a processor that you can customize and add this technology. So that's what we were trying to do. What we did initially was putting the actual processing unit inside the CPU, so inside, in that case, the CVA6. That's our initial proposal of PERCIVAL. But we also want to work on modular solutions. So instead of having to get inside of the CPU and try to see where we can put it and how we have to connect it, to have an abstract layer that has in one side the CPU, in another side the POSIT arithmetic unit, and somehow connect it together, but they're still some separate, right? This would simplify all of the process that we had to do of getting inside of a CPU and exploring how it works. The thing here is that we need expert knowledge in hardware design, computer architecture, and this is basically some work that you have to do either at university or at tech companies that have the knowledge for this hardware design, right? And not only this, I mean, you have a CPU, but you need to be able to run code of that CPU. And each CPU is different, so we actually needed new compilers, which are the pieces of software that translate a code into actual binary numbers, into actual zeros and ones that are then executed on a CPU. So since we modified the CPU, we added new POSIT functionality, new POSIT instructions. We also had to modify, in this case, LLVM is a compiler for C code that maybe some of the audience knows. And we added Exposit, which is a custom RISC-V extension for POSIT numbers. So now we were able to compile C programs together with POSIT instructions and run them on our actual hardware. And since we've benefited a lot from it, and we also want people to be able to explore the use of POSITs in our hardware, we also open sourced this modified compiler. You have the URL there, and you can translate your own POSIT programs down to binary code that, for example, PERCIVAL can understand and can run and can give you actual outputs.
Okay, so perfect. We have learned a lot about your technology, your developments, and the POSITS technology. And the end of the interview is approaching. I just want to ask you a final question. So, has anyone been interested or approached you some way? It's too early probably, but did you rise some interest in the industry or in any other groups, or what?
Yeah, I mean,
Can you
actually,
say?
in the research community, and not only research but also the electronics, the engineering community, IEEE Spectrum, which IEEE is the largest electrical electronic engineering association in the world, if I'm not wrong. They have IEEE Spectrum, which is a specialized magazine, a specialized journal that ships all around the world, that actually interviewed me a few months ago, and this was published both online and also in the paper, in the actual magazine that they distribute to all of the members. And also John Gustafson, the inventor of POSITS, like last month at the Congress of New Generation Arithmetic, in his welcome speech, he was talking about our contribution in this case, because for the first time, the largest conference in arithmetic in the research community was accepting a POSIT-based paper, a POSIT arithmetic paper, which was our proposal in PERCIVAL. And then he also said that the IEEE Spectrum article had 64,000 reads in 24 hours, which I can still not believe. And we went to print for 300,000 readers back in December. So even the inventor of POSITS catched our hardware designed and was promoting our work. And then also the pull platform, as you can see in the bottom, this is a tweet that they sent a few months ago when we presented PERCIVAL, because we used CVA6 Ariane, part of their research, and then we modified it. We added our arithmetic, and then we gave it back to the community, and they also decided to give us some visibility in this, and also some specialized blogs have shown their interest. So it's actually a quite hot topic that could have a large impact in the future.
Absolutely, and I was moving because I was looking for this issue. Probably you know it because
yes.
There is here inside the article is speaking about the I don't know how it reads. It's POSITS, and it's speaking about you as a group, and it's speaking about you. I'm showing to the camera here.
Yeah, somewhere in there is my name.
Yeah. In the article, so it's a good reference, and I have to be honest. I received this magazine. I'm the senior member of the IEEE for more than 10 years, and I knew about you and your technology by reading this issue, this journal. So congratulations, David, and congratulations to all your team. We have reached the end of the interview. We need to finish it now to let our audience and our sentinels to have dinner and to finish the day properly. And if they are watching this in the recorded version, I also recommend and remind you to subscribe to the channel. The Tower is a channel for everyone who wants to know about technology and edge technology, what is there and what other media are telling you about what is coming regarding technology. So thank you, David, again, and congratulations for your work, and congratulations for explaining everything so clearly. It's a very complex topic. It's a highly technical innovation, but you explain it successfully to all the audience, and I hope you understood it properly. And we will put some links in the text of this video. You can also add comments and we will check it. If you have more questions and you are watching this offline, you can leave comments and we will hand them over to David. And again, as I told before, we are the tower. We are the place where we are watching technology for all of you to get it close to you in an understandable way and for everyone. Thank you very much.
Thank you very much for having me here. It was actually a pleasure to be with you. I was also surprised to see the IEEE Spectrum magazine there. That was a quite surprise to always see. And to everyone, yeah, feel free to reach out to me if you have any other questions. My email was there. And yeah, if you have any questions, if you have any contact that you want to if you want to get in touch with me, please feel free. And yeah, so thank you very much again, Antonio, for having me.
Excellent, excellent. So we finish now. I just wanted to add, I said it before, today is a big day for me because my next book, my latest book is being published, officially published today in the US. It's available worldwide because the editor, Business Expert Press, is distributing worldwide in all libraries and Amazon, of course. So if you look for Metaverse Antonio Flores in Amazon, you will get my book and you will be able to order a copy. And I'll be glad to hear your comments about the book. And I'll be glad also if any one of you watching this video want to suggest new topics or new interviews, or maybe you want to be interviewed in the next chapter of the tower. So feel free to contact. The URL is here on the top right of the screen. And I will be glad to hear from you. Thank you very much and see you in the next chapter from the tower.